As a robot moves, it creates new poses. Using sparse range sensors, the robot scans new points, which are used to extract lines. The lines are merged into existing landmarks, or create new landmarks if necessary. New poses form pose-landmark constraints. Landmarks also form constraints with each other, called landmark-landmark constraints. The pose graph uses relative poses from the landmark graph to perform loop closure. When the robot revisits a previously visited location, a loop closure constraint is added. We run various datasets using SoMaSLAM and EG-SLAM. A deciding factor in the relative success of SoMaSLAM compared to EG-SLAM is the accuracy when mapping the C-shaped section. The soft Manhattan world assumption, enforced through landmark-landmark constraints, improves this accuracy. We now run the MIT-Killen dataset using 4 points out of the available 180 points. Due to the lack of points, EG-SLAM fails to perform a loop closure. SoMaSLAM successfully performs loop closure thanks to the effective landmark-landmark constraints. We now run the Intel Lab dataset using 4 points out of the available 180 points. For the Intel Lab dataset, EG-SLAM fails to perform loop closure, whereas SoMaSLAM successfully performs loop closure. We run our dataset collected using a crazy fly, which we call library 1. SoMaSLAM embraces the Manhattan world structure of the dataset, and as a result, performs better than EG-SLAM. We run another dataset collected using the crazy fly, which we call library 2. Rather than comparing SoMaSLAM with EG-SLAM, we compare SoMaSLAM with FL-SLAM. FL-SLAM cannot map non-Manhattan worlds, as it is only able to create walls that coincide with the Manhattan world. When mapping the diagonal wall at the top, FL-SLAM creates walls that do not represent the actual wall, but rather align with the initial Manhattan world. SoMaSLAM has no issue mapping this dataset.